Hello and welcome to this fourth webinar on error handling. I have been going through the basics of error handling in Dyalog APL in previous webinars. A quick overview is in order before I'll show you what I'm going to speak about today. In the first part of this mini-series, we looked at the very basic parts, the control structure, the error guards, and basic error numbers. Part 2 was about the more advanced ways of trapping and getting more information about errors. And part 3 was on how to throw errors, to raise errors themselves, and how to propagate errors further. And we also looked at assertions. You can find these on dialog.tv. What we're doing today is we're going to look at more practical applications of this. So when you make some big program, then there are various things that can go wrong, and we're going to look at nice ways to code in preparation for such situations. I'm going to distinguish between errors that you should have anticipated as you write your application, and errors that are mistakes as a programmer and that you didn't expect to make a mistake, of course. When you are debugging an application, then you don't want the application to handle all the errors, so we're going to look at turning that on and off, and we're going to look at giving the user, or for that sake the developer, and a report about the error and how to access that. Then we're going to have a look at raising errors inside threadfins, and how dfns can give you unexpected behavior if you're not aware of exactly how they work when it comes to errors, and how to deal with those issues. Without further ado, we are going to be using a tiny application as our example of code that will have bugs in it, and what the behavior will look like when we hit those bugs. This is our application. It's quite simple. It is a monadic function. It takes a file name, gets the file's content, converts the text there to UTF-8 byte sequences, one per line, and then converts those numbers, which are numbers in the universal character set, to well, no, they're not numbers in the universal character set. They are bytes for representing in UTF-8 the numbers into the universal character set. And those bytes will then represent them in hexadecimal, where digits above 9 are alphabetical, like is common usage, with a space in between each. So one line per line in the file. Let's try running it. So we create a file, a text file that contains a couple of lines of text, and then we run our application, and we get a nicely displayed result. So that looks ready to go. There's just an issue. Once we ship this to the end users, they might try to run the application on one of their real files, and all of a sudden APL suspends with a tracer open, and yeah, maybe we were deploying a little bit too fast. So if we have a close look, we see that they spelled customer wrong, and this is the type of situation that I, as a programmer of this application, should have anticipated. It's not a logic error in my code as such, but I should have expected that the user didn't quite use the application correctly, didn't check that the file exists. And I should put in a note here. In my opinion, I think good coding practices for APL is to check all our assumptions before we continue, rather than relying on trapping any error that happens and continuing. But since this webinar is about error handling, that's the approach we're going to take here. But again, clearly the application could have checked does a quad n exist, could have checked does the file exist. If not, then tell the user that that's not right. But yes, we should have anticipated that the user could give a name of a file that doesn't exist. How can we handle that using error trapping? Well, let's make some space for additional code. And then we add the colon trap control structure as we've seen before. And the else clause here, we are doing a tiny resignal. So trap 0, as we learned in previous webinars, that's trapping all the errors. And quad signal quad en is the poor man's resignal. It just takes the error type, the basic error types, and throws another error up the stack using that. And we can do that way more sophisticated, but that was the previous webinar. I won't clutter our code with that for now. So now, when we try this again on a file name that doesn't match any existing file, we can see that we didn't get suspended inside the application, rather we threw an error, much like as if this application had been a primitive in APL. It's a sealed box, which is nice for the user, and then they could trap this or just use the error message and so on. But if I want to go and debug my application and add features to it, so on, then I might not want all errors to just be trapped and reported. I would rather want the traces to come up. And it's not so nice to have to modify the source code to change this behavior between development behavior and deployment production behavior. Instead, we can build into the source as a sensitivity to a setting, so we don't have to modify anything. We can just change the setting. And so this is turning trapping on and off. Looking at this code here, we make some space for a setting. So notice that we have here a function inside a namespace, and I'm adding a member to the namespace, which is just a global variable, which normally you wouldn't use global variables, you would be functional, pass around, but this is really a type of state of the environment. It's not a parameter to any function. And then if we look at our trap statement closely, then we see it says trap 0. That's an unconditional trap all errors. We change this to using the debug variable. Now, if the debug variable's value is changed to an empty vector, then, and remember that trap takes a scalar or a vector of error numbers that it should be sensitive to. If we give it an empty vector, then it's sensitive to exactly no error types, and that means that the trap is effectively disabled. We could also set debug to a specific set of errors that we are interested in the application handling at this point, whereas all other errors will cause a suspension. However, even more versatile than this is modifying it like this. So we use the debug rather than a value for the error numbers. We use it as here a boolean. So if we set debugging to 0, 0 drop 0, that gives us a one element vector with a 0, so we trap all errors. If we set debugging to 1, so we set debug to 1, Then 1 drop 0 gives us an empty vector, and we're trapping nothing. So now we have a flag, whether we're debugging or not. And the real cool thing about having the debug variable inside the namespace script like this is that while we can say app.debug and set it to a value, the script itself doesn't change. And so if the script comes from a source file, for example, that doesn't get changed just because we're changing the value. We're temporarily overriding the value that's in the script. That means you'll never end up in the situation where you ship something off and you forgot to take out the parts that were there for the debugging. Because as soon as somebody does a fix, as soon as they import this code, they run this code, it will always set debugging to 0. You have to always go and set it to something else in order to get a different behavior than the default one. Now if we continue testing, we can see that the behavior hasn't changed for the bad file name. We handling that, but now we're trying it with a different file with some other text in it, and boom, we did end up in the tracer. And why is this? Well, we can, since we're suspended, we can look at the bytes here and represent them in base 16, and then we can see that there are some zeros in there, and we hadn't changed the default quad.io to 0, which is otherwise something you would want to do when you are working with number bases. And that of course means that for all those zeros we are trying to index into our list of digits and letters to position 0, which doesn't exist, so we get an index error. Making a quad.io error like this is of course very common, but it's not something you would expect yourself to do. It's simply an oversight. And unlike the missing file, which we could have gone and detected using quad.n exists, this is not something that you could code for. This is really something where you need in an end-user application to have a trap so that the user doesn't end up in a strange state. So how do we do that? Let's make a little bit more room for some more code, and we add another trap statement around everything. So notice how this trap doesn't just go around the single critical line about getting the file, but rather goes from the very top to the very bottom. And while really it's bad practice to just do a blanket trap 0, trap all errors, because that will prevent you from seeing exactly what's going on and fixing your bugs, because the application itself will try to handle everything automatically. For a global error trap around everything, the outermost layer in an end-user application is probably a good idea. But make sure the user gets a nice error report as well. And this also means that we can tweak our debugging, because let's say we're debugging the application for these unexpected errors. It's very annoying whenever we try to throw a test case at the application code that the application actually does know how to handle the error condition. So we give it a bad file name. It would be very annoying if it would then pop into the tracer every time we give it a bad file name when there is no issue. It should just handle that error and continue. So you can see if we set debug to 0, then we trap everything. If we set debug to 1, then we trap nothing. But we want an intermediary state. And we can do that by changing the inner debugging statement, the inner trap condition here, to have 2 zeros. Now debug isn't Boolean anymore. Now it's a number. It's a debugging level. So if you set debug to 0, or leave it as a default, then we trap everything, including having additional trap at the middle of the function where we resignal out. If you set it to 1, then we disable the global trap, but the expected errors are still being handled by the inner trap, because we do 1 drop on 0, 0, that leaves still one more 0. So we're trapping all the errors there as well. And we can actually be even more sophisticated. We could write something like this. So if you set debugging to 1, we still preserve 1 and 22. So 1 and 22, those are workspace full and a file error, and there could be many different errors. So you could pinpoint exactly with which values of debug do we want to trap which types of errors. And you can be as sophisticated as you want here. In fact, you don't need to have one debugging variable. You could have various types of debugging variables with various types of values and combinations of them with some logic, and you can get exactly the trapping of things that you want to be trapped in when you're doing your work, and not trapping other things that you want to show themselves. So these are just some examples of things you can do, and you probably don't even want a trap 0 in the inner trap here around getting the file. Again, it's better to check for the existence of the file, but you might want to trap various file related errors, but you don't want to trap, say, a syntax error. That would be because your code has a problem. And then we want to, from the global trap, give the user a nice message. If you used computers enough, then you've probably experienced some application popping up a little message box saying, oh, we hit an unexpected error, or maybe even please wait while we notify the developers or something, sending an error report, that kind of thing. Or the application quit unexpectedly and an error report is saved at some location, or we've done a memory dump or something else, or we have to restart because something didn't work out right, but don't worry, all your data is safe. Or some further instructions to the user. We're just going to do a little bit here. We're going to throw an error, and notice that the error number I'm using here is not the error number of a normal APL error. Rather, it's a custom error number, and that means we could write documentation for our application and saying, under these conditions it will throw an error with this number. So these are usually numbers in like above 200, and under these conditions it will throw this error, and it can help the user to look up in the documentation or contact the developer and say, hey, I did this and this, and I got an error number 256, what should I do? That kind of thing. So now we have our debug levels. Let's see how this actually looks. In the normal circumstances, we have the inner trap catching the bad file name, and the outer trap catches our quad.io mistake. If we set the debugging level to 1, then we give the bad file name. We still have the inner trap in effect, but the outer trap has been disabled, and so when we try to use this file that has a character that causes the index error, then we pop up the tracer. And if we set the debugging level to 2, then even a bad file name will let us debug that. So, and of course, using the file that causes the index error, it has the same behavior as before. But as I said, we could tell the user more about what went wrong rather than an unexpected error happened, click OK to continue. And we do that by, before we do the quad signal 256 in this case, we collect some information about the state. So let's make room for that. And remember, quad.dmx returns this namespace with error information. And we can just catch that. It's important to catch it. We can't just tell people, oh, look at quad.dmx. Why not? Because as soon as you do a quad signal on the next line, that itself is an error that happens, and therefore the namespace that quad.dmx had gets discarded and gets replaced with a new namespace with the information about this new error. So it's going to have error number 256, and it's going to have the EM error message, unexpected error. But this message here, it will refer the user to app.error. Since error is a global name, it's not localized in this threadfin, then this namespace that QuadDMX has returned gets stored inside the app until the next time such an error happens. And it's important to catch the value of QuadDMX as soon as we can, because if there's some of our error handling code that itself hits an error somehow, then we would have lost the old information about what went wrong. So that's the first thing, and then you can do various processing afterwards. For the details of QuadDMX, see the second part of this series. Now let's try it. We get an error here. This was being handled by the file name error handling thing, and then for the actual application code error, then we get the message about the unexpected error, a reference to app.error, and then we can do app.error. It's a namespace, of course, so we can say what's the diagnostic message from that, and we can see the code that went wrong. Now this might not be useful for the end user, but you can imagine how we could take this and ship it off in an email or something like that to the developers and saying, oh, you got this. So we could serialize this namespace with all its members and then send it off like that. And also, because it's a namespace, we can actually do a bit more. If we focus on this line where we catch the error, and we could take this namespace and populate it with even more members than the ones it has by default. So here we're adding the file name and the bytes that we have gotten. Now we have a question: how does this scale for an application? Right, if you wanted this in all kinds of places, it might become a significant part of your source code. But in the error trapping clause, rather than in each function itself or each user-facing function have all this code, you could just call an outside error handling function and propagate all the values to it that you want, including all values. You could even, if you're jumping from namespace to namespace, you could even give it a reference to the current namespace, and then you could inspect all that and serialize. So all you need in every top level function is the global trap and then maybe one line that does a call out to an error handling function, and then you do everything over there. So all in all, it adds what, 4 lines of code. So we put this back in with the extra information, and now when we hit our error, then we can look at the bytes in the error namespace. Great, this was all threadfins. What about dfns? So for dfns, you have to watch out a bit. It isn't so simple to just translate this type of code to a dfn. Let's try it and see how it can easily go wrong. So here's the outer structure of our hex function, and then we take our actual application code and put it in here. And the way dfns work is that we set up error guards. So it would be natural then to propagate over these 2 traps to be error guards. So first we set up the global guard, and then we set up the more specific guard inside, with the intention that the inner error guard only applies to our file fetching code, just like the trap structure in the threadfin only applies to the file fetching code. The only problem is that the way dfns work is that as soon as you set up an error guard, it applies until the end of that dfn. It's not a structure. It's just kind of like a declaration. So it will apply even to later code, which means that when we have this 0 here, that should really only be the inner trap, that's being handled by propagating to the user the message about the error, the file missing, what in fact ends up happening is that any subsequent error will be handled by that 0, and we can never reach the first error guard we set. It's, so to say, being shadowed by the inner one. So that doesn't work. Let's try again. If we take our application code and then instead we put our specific guard at the top so that it takes effect for the file fetching code, and then we put in our global trap after that so that it overshadows the old error guard, then it will seem to work. The only problem is that if we drop one element using debug, then we still have 1 and 22 in our case applying. And since we have dropped all the elements from the list of error numbers in the bigger error guard that's below, then we're not shadowing anything, and that means that any error 1 and 22 that's being hit in the code subsequently will skip up to the error handler that was really only supposed to be for this localized line. And not only that, if we had any preparatory code that would have to happen before we go and fetch the file, say normalizing the file name or something like that, then we wouldn't have our global trap for that either. So this whole approach doesn't work. Rather, what we can do is we set up a different structure on our function, where the file fetching is happening in its own inner dfn that lives inside our outer function. Because remember, I said when you set up an error guard, then it applies until the current function is gone. And so here we set up the error guard in the inner function, and then we do just the work that should be affected by that error guard, and then we leave that inner function, and that error guard is then dissolved, and we fall back to the higher up error guard from the outer function. And how would we collect the error information in dfns? Well, that's when things start getting a bit hairy. Let's think about it. In the transfen, we added this line of code that was executed as soon as an error happened before we signal further. But if we compare that to what happens with the error guard, then the error guard, so to say, sets up a new scope. It's saying from here on out, this is the point where we fall back to if any of these errors happen. So while we apply to the entire area there, and then an error happens, that scope is rolled back to where the error guard was set up, and any assignments that are not global outside of the function or to some namespace disappear as well. The whole scope is taken away, including our assignment to the variable bytes, which means by the time we reach the code in the error guard, it's too late. The bytes are simply not available anymore. Now this sounds strange, I know, and it's a bit obscure here because we're in the middle of all our application code. So let me give you a minimal example of this. Here's a tiny little dfn. It seems to be very straightforward. First we assign A, then we set up an error guard. If any error happens, return A. Now we change the value of A, and finally we cause an error. $sign doesn't mean anything in APL, not yet at least. And we would expect then that execution continues at the error guard, returns A, and A has been set to the value 2. So we expect a 2. But in fact what happens is we get a 1. What happened? When the error happened, we rolled back the state to when the error guard was set up, in the process eradicating this new assignment to A, and the only value that that persists of A is the one that was before the error guard was set up. So this is something to be aware of for defense. So how can we do it instead? Well, we need more space. We can start by setting up a namespace where we're going to keep our information. Now, since this namespace lives in the scope that's before the error guard, then it's not going to be erased when we roll back to where the error guard is. So we use this namespace to hold our data. And then we can set up a handler function, and the handler function is then called at the error guard. This is because we need multiple things to happen, and an error guard would otherwise quit immediately. Then when the error happens, the data is preserved because it lives outside the scope of the error guard. It's passed on to the handler. The handler also lives outside the scope of the error guard, and it can then use that data to generate its error report. But yes, this is pretty hairy. And as you can see, if you're doing advanced application programming, it's not moderately advanced even, you're probably better off using a threadfin for this kind of structure. Defins are fine when it's all functional and beautiful, but when it comes to this kind of flow, it gets very complicated to get it right. Even more so if you consider capsules. Let's talk about capsules. It's easiest to illustrate actually with a threadfin, even though it makes not so much of a difference there, and it probably just works the way you expect it to. But if you look at the details, it's kind of interesting what happened when we used quad signal inside a threadfin. So let's call this inner function. What happens is we set up a trap to trap all errors, and then we use quad signal to create an error. And funny enough, the trap is being ignored, and quad signal succeeds in bubbling up the error. So we can see the behavior quad signal, its name is actually very good. It's not throw an error, raise an error, or just error. It's a signal out of the current capsule, and a threadfin is its own capsule. How can we see that? If we add another function, oops, it's a bit funny. Sorry about that. Okay, something is not quite right here. Well, what I wanted to say was that if we added another function, then we call the inner function from the outer function, then even though the inner function's trap is being ignored, if the outer function also has a trap, it will catch the signal from its subroutine. Sorry about the slide not being quite up to spec here. Now, if we look at defense instead, then let's focus on the actual code that's dealing with the error. We use the read function, and that goes up here where the read function is defined. And the read uses quad signal, but in a dfn, then any other dfns that are defined inside, whether they're given a name or whether they appear literally just unnamed inside, they're all part of the same capsule. And therefore, when we hit quad signal, we also ignore any error guard that's in that same capsule, and quad signal succeeds in bubbling up the error to the caller of the outer capsule. If instead the read function was defined outside hex, then it's its own capsule, which means when we call read and it then does a signal, then the signal will be caught by the error guard that's in hex. And that means that we call the handler, which wasn't for this type of problem at all. How can we fix this? If we enclose the call to read in its own little scope, then we already have something that can catch the error signal by read just specifically for this, and then we can resignal, because this creates a tiny little error guard scope. We call read, and then read uses quad signal, and it's being caught by that little error guard, and then we take that error and propagate it further out. And now, because we are using quad signal inside the capsule of hex, the signal is able to leave all the way out of the outer capsule. And yes, this is complex. Again, I would not recommend using dfns for this kind of thing. If you're writing an application, at least have a top level threadfn that takes care of handling exceptions that might occur as the application runs. And then you can use functional programming with dfns for all the data transformations and manipulations and so on. But can it be done in dfns? Yes, it can. You just have to really keep in mind what's being called from where, and what is the scope of everything. And with that, this is what we went through today. How you can set a level of debugging, and you can use APL expressions to adjust exactly which errors are being trapped at what point, and how we can collect the error information from the error that happened and use that in various ways, and the warning that if you're using error handling inside dfns, you want to be really careful about it. Don't forget to test your code. If you have any questions, now's the time to ask in chat. I'll give you a couple of minutes for that. And while we're waiting to see if there are any questions, here is an overview of upcoming webinars from British APL Association. The next BA meeting is a special one because there are some amendments to their rules that they wanted to get through, and so they're being discussed and voted on in this next meeting. We have a question from Devin, whether quadtrap can be used inside a dfn. Yes, quadtrap can be used inside a dfn, and it will work very much like what we've seen in the earlier webinar on quadtrap. However, if you're using quadtrap inside a dfn, then you shouldn't use error guards at the same time. you'll end up with some strange situations if you do that. So use one system or another. But again, quadtrap you should probably only use if you really need that kind of fine-grained handling. Okay. Thank you very much for watching, and I will see you in 8 weeks for part 5.